Okay, so good morning, everybody. You're with Dr. C, and let's graduate with Madame Farah Farshour. I'm so happy and honored. I will not make it long, but I cannot not to talk about it. So I'm so happy and honored that we're participating to this second meeting together, Zoom meeting, virtual travel to the space. So you're not done yet with me and with us. We're going to talk today about the exoplanets. We're getting extra, but by saying extra, we're really getting extra. So we're leaving. Seriously, we are going to leave the Earth. Last time, we talked about the astrophysics, astronomy, and we spoke about how to do astrophysics, why astrophysics is a passion, why we're not and never get bored with that. And we spoke about the ISS, and we went to the ISS, we went to the James Webb. But today, we're going to be more specific. More specific, I mean that we're going to go to the extrasolar planets. So take your suits and come with me. I'm going to open that because it seemed that it didn't open it. And you are going to be with me. I'm trying to do something. I hope that it's smart. And let me share that with you. So I'm going to start by the first discovery of the first exoplanet. Okay, so I'm sharing it, and please, Farah, tell me if it is shared, just with your hand. Okay. So I wanted to have you know, kind of spices. This is our extraterrestrial. Oh, it said that my high CPU usage is affecting my meeting. I don't know what is that. So it's affecting my slides. I think that we have things here, but it's okay. I'm continuing until it crashed. So here our neighbor, the alien, is taking the Earth with his hands. And I think that in the time of Corona, we all hope to leave our confinement. But anyway, so in 2019, things has changed with the exoplanets. And for the first time, the Nobel Prize in Physics were given to two of the persons, Michael Mayer and Didier Queloz, the first discovery of extrasolar planets, not the first extrasolar planet, but the extrasolar planet that was and still rotating around a star like our sun. Because bear your mind that the first extrasolar planets were discovered in the 1993. It was around a very weird star, a pulsating star. And we were really very surprised because since ages, we were thinking that maybe we will discover a planet outside our solar system, but it has to be like a sun like ours. And here you go. In 1992, 1993, they discovered a planet around a very explosive, pulsating thing. And they said, no, there's something wrong. And in 1995, Michael Mayer and Didier Queloz is the youngest one. He was a student of Michael Mayer. They were just doing a test. And Michael Mayer, for the story, Michael Mayer went to the 1-year sabbatic to Hawaii, and he let Didier do the study. He was a student, and he told him, don't think that you will discover an exoplanet around a normal sun like ours. But, you know, if you don't discover it, you will lose your PhD. And Didier Queloz observed several times. He said that I am discovering an exoplanet. I will tell you later how. But he said, no, it's not. He said, my mentor told me that I will not discover it. It's not efficient enough. He measured it twice. It is the same result. He measured it 3 times. He is having the same signal. He called his, you know, there's no MSN, there's no Zoom, there's no nothing. He called on the phone. He said, doctor, I think I discovered an exoplanet around a regular sun. He said, yeah, go ahead, let me sleep. And then he observed it 4 times. You know, in science, to be able to say that you discovered something, you really have to observe it several times. Then Didier said, hell yeah, I have to tell him that I really discovered an exoplanet. So he phoned for the second time Michael Mayer, 1995. Then Michael Mayer told him, well, maybe you really discovered an exoplanet around the sun. And this is how they discovered an exoplanet. So you might tell me, since 1995, why now in 2019 they gave a Nobel Prize? Well, normally the Nobel Prize is not just for the discovery itself. The Nobel Prize is for the legacy after, is for what التبعية، يعني شو بيعملوا بعدين، شو بيصير من وراها, what happened. And for the first discovery until now, so until now we have this, means that the first exoplanet was discovered by this small telescope, the OHP, by those two Swiss. And this is an artist's view of Pegasi 51. And from the first we have now, it is done, this sketch yesterday. Today I didn't have time. I am saying, emphasizing that it was done by yesterday, because you may know by now, as I told you last week, that every second we might confirm a new extraterrestrial planet. So from 1995 until yesterday, we have 4,144. Do you remember last week we had 4,141 extrasolar planets? So in 1 week we have 3 more confirmed. So from 1995 until today, we have 5,075 candidates. We have 3,774 planetary system, means that planets around another solar system. So this is what happened. What happened is that we have satellites just rotating around the sun, and we have those histograms. What are we seeing here? Oh, I'm sorry, maybe you're not seeing exactly the right numbers. Here, you see this is in x-axis, we have the year of discoveries and the number of planets discovered. You see that in 1992, we have 1, 1995, 1 other, and you see in 2000, 2016, 2017, what happened here? We have Kepler and other satellites. So you see the bump here in 2016-17. So this is what happened. We discovered terrestrial-like planets. We discovered giant. We discovered fantasy planets that our science were not able to imagine, means that we discover planets that normally doesn't have right to exist. We are used to in our mind to have the giant planets outside the solar system, means that after the asteroid belts, and we know that the rocky, the solid ones, inside the asteroid belt. But the universe showed us with our discoveries and the data science that we can find giant ones near the suns and very small rocky one very far. And also several flavors of the exoplanets. We can find big one that they are wandering around, we don't know what suns, what stars, lonely planets. So this is what happens, and this is the legacy of Kellos and Mayer. And when I'm saying that this is Kepler, oh, it's not rotating, but it's meant to be a movie. I'm trying, I will try to do something. If I do this, okay. Oh, still sharing. Is it rotating? Oh, super. Okay, it's rotating, Farah. Yeah, you can say this. Are you seeing a movie? Farah, it's not rotating? Is it just an image? Okay, it's a shame. Fine, anyway. So what you normally you have to see is that Kepler is, this is Kepler, the Earth and the Sun. So the revolution that was made with the satellite Kepler, you can go on the YouTube, Kepler mission NASA, and you can see Kepler turning with the Earth. So Kepler is rotating with the Earth, and it was just observing one spot in the sky near the Cygnus. And with that, Kepler did a great job. So I will show you the field of view of Kepler and the method that Kepler used. The method that Kepler used is called the transit method. The transit method is one of the simplest methods to discover exoplanets, simplest yet not that simple. But this is not just the characteristic of Kepler. The characteristic of Kepler is that it gave us a lot of data to analyze and to know if it is a giant or if it is a rocky one. So Kepler looked at, we will go back in the method of detection in a few seconds. So Kepler looked, let me show you and I'll come back later on. Kepler looked at one spot in the sky. You see here the galaxy center, and it looked at a one spot. What you are seeing, the squares here on the image, it is what we call the field of view for Kepler. What is a field of view? It is the spot where Kepler always looked in the sky. Means that for several years, Kepler spotted this only and one single only spot in the sky. And it observed it for several times with the transit method. We don't know, we had no clue about if we are going to observe an exoplanet or not. But as you remember from the last week, we said that the formation of a star is very simple. يعني banal, هين, بايخ. So we have this cloud, it will collapse, and then when at collapsing, it will trigger the nuclear reaction. When triggering the nuclear reaction, we form the star. At the formation of the star, a big explosion, and we start to form the planets. This is why we scientifically believe that half of the stars have planets around them. So we take Kepler, we put it in the sky, and we observe. وخدوا التباديع شو اكتشفنا. So with that, we discovered until now, with the method of observation, that number. We discovered, as I told you, until yesterday, 4,144 exoplanets, 1,389 size of Neptune, 1,304 giant. Listen well, very well. عندنا 161 terrestrial-like. And here we are approaching to the habitability, search for extraterrestrial life, exobiology, exochemistry, and we have also 1,290 something super Earth. Super Earth يعني بيكونوا هن rocky, but 4 times Earth, 5 times the size of the Earth. So you see that from one extraterrestrial planet around a sun like ours to 161 terrestrial-like. So we are really now having a revolution with a lot of data. Those 4,144 extraterrestrial planets we discovered, you see, when I told you that the transit method, and I will explain to you in details later on, is kind of the easiest way to observe. We have 76% observed exoplanets with this method, 19.2% observed with the radial velocity, means like Doppler effect, 2.1 fantastic microlensing, we'll come back later, 1.2 it's direct imaging, as if you are taking a picture of the exoplanets. We will come back. You see that the transit method is somehow the most effective way to detect the new world, the extraterrestrial world. And it is one of the reasons that the James Webb Space Telescope will also search, entre autres يعني من الطرق الأخرى, the transit method. So the James Webb will be also searching for transit and spectroscopy and direct image. We will come back. I just want to remind you that all those 4,144 confirmed, 5,000 candidate, 3,000 extrasolar planetary system are just in here. We are in our galaxy, and it is just in this small spot. You see? So we are just babies in understanding the extraterrestrial world. I'm not talking bad yet about extraterrestrial life. So I repeat, you know, we sent Kepler like 11 years ago or 10 years ago. We observed with Korod, with other, with HST. We were so happy we discovered terrestrial planets. بس روقوا. We are just observing here, okay? Yani as if we have, I don't know, the universe is ملعب football, the whole universe, and we are just observing in one corner بحبة وحدة صغيرة هيك, ها هون, and we are finding 4144 exoplanets هون, وبعد ما عملنا كل الداتا analysis هون بس, ها imagine, okay? So I'm just, why I want you to visualize that we don't know anything yet. And the best is yet to come. So the mirror of Kepler is 1.4, if I remember very well, 1.4 meter. And you saw in the image, in the picture that I showed you for Kepler, it is completely near the Earth, right? So it's not rotating around the Earth, it's rotating with the sun. It's so polluted, and it's a shame because I cannot show you the deployment of and the orbit of James Webb because the movies are not showing, but it's a really piece of art. So I really encourage you, and I will talk with Farah when we will upload the video. I will put 2 links for you to see the orbit of, because it's a really gold technology, serious, and it is gold, the mirror is gold. And you will see that the orbit of James Webb, you will see the technology, how to observe with it, and the method. So it's a shame it was a 2 minutes minus 4 seconds movie. So the deployment of the shielding, how the mirror will open, and how it will go to the orbit L2, right? So now let us talk about, it's useless to show you images that are now.
Can we just make full screen of the PowerPoint?
Full screen, yeah, of course.
No. I'm
just running them like this. So those are the observatories OHP where they observed the first time. This is a Pegasus 51b. Those are the number of the observed, and I will keep the answers, the questions for later. You see the peak of the observation when we had Kepler, the number of, this is Kepler, the satellite moving with the Earth, observing in a transit. Those are the method and the statistics with the observation that I'm going to explain now. This is the field of view of Kepler. You see that it's a really small part in the Cygnus. So you see that here, whatever we observe is just in a small portion in our galaxy. And now I am seeing it a movie, but you're not seeing it for James Webb. And I thank you for telling me, because it's not beautiful if it's not very big, okay? So here I'm going to go directly into the method of detection of exoplanets. So as I was telling you in the number of exoplanets detected, we have several methods. Here, I'm just going to detail the most important scientifically and efficient methods. The first one, what you're seeing here, I would like if I have a conversation, but I know that technically it's not possible. So I will repeat it. I hope that I will repeat it. Yes, is this okay? So this is what you're seeing. It is, no, it didn't repeat. Let me just do it like this. This is the radial velocity. Radial velocity, if you may understand it easily, it's, oh God, I need to, it's just technical. My screen stopped, 1 second. So the radial velocity is like Doppler effect. If you have a very massive star and a small planet near to it. So what happens? The thing that is happening, the star is rotating, the star will emit wavelengths. The planet that is near to it will really influence the wavelength that is emitted. So normally you will have, if there's no planet, the star that is emitting a regular frequency, you know its frequency. But when you have a planet near to it, this frequency will be shifted. So what is shifted? يعني كأنه لقطتها. So it will be, if it's going towards you, it will be shifted towards the blue. We say the blue. And if it's going away to you, it will be shifted towards the red. يعني كأنه بالأمبولانس لما نسمع نحن it's kind of Doppler effect. So when we are going to observe a star, we don't know what's happening, but we can see that her normal frequency, regular one, it is not the same. So there's a difference between the nominal, theoretical, and what we receive. So this is how we can know there is a planet or not. The second one is called astrometry. Astrometry is very difficult. Why? Because it needed a very high precision. So normally a star, when it's rotating, it rotates like this around itself. So it rotates around a point if there's nothing around it. But when there's a massive object around it, they will rotate around a virtual center of mass. So what happens to the center of the star? It will not rotate around its axis, it will wobble. It will do like this. Why? Because as the gravity tells me that two objects, big objects, will influence each other. So the force between them will be really the same. Even if the star is so big, it will really wobble a little bit. Her center will wobble a little bit. We developed technically detectors that can really measure the small change in the center position of the star. You see how technically it's very difficult? And we can know if there is a star, a planet or not. So the third method is the direct imaging. To do a direct imaging is also a technical challenge. The direct imaging, you cannot just take a picture when you observe Jupiter or Saturn. Why we can take images from the solar system? Because we are near. The solar system is like our neighbor here. But if we are observing a star that is billions of kilometers and billions and 30 light years, 50 light years, we cannot take a picture of the planet.